So good morning, good afternoon, good evening to everyone joining us for this month's NfoLD seminar. This month we have David Avnir speaking to us. David is from Hebrew University of Jerusalem, and I'm very excited for his talk because we've had a lot of conversation here of late, including last week through the joint NfoLD Nexus workshop on standards of evidence in life detection. But in astrobiology and life detection in general, we've been discussing for quite some time chirality as a biosignature, chirality as something we can use in looking for life out there. And so David today is going to give us a lecture about using chirality as a biosignature, as a tool in life detection, and some of the weaknesses and strengths of chirality as a potential indicator of life out there. So I see more are joining us, thankfully, right now. Others will probably join us here in a moment. But without wasting any more time, David, the floor is yours to take us away on this journey of chirality.
Okay, thank you very much. Can we remove that strip on the top because I think it's covering the slides? Or
I don't see it from my end.
You don't see it, then in that case, okay. Okay, so good evening, good morning, everyone. And I'll be talking today about chirality indicators of extraterrestrial life. And let me start with the motivation. Actually, I think that this audience does not need a lot of explanation of why is that important. So just one slide that summarizes the idea. And the motivation is mainly that the exoplanets revolution. I think that many of you, or most of you, were born into a universe which contained only 9 planets. And today we have significantly more than 4,000 planets. And that is really a very deep revolution, not only in astronomy, but it has implications in science, in general, in philosophy, in social impacts, and so on. And the reason is very simple. Suddenly, the prospect that life must be widespread beyond Earth seems ever so obvious. If you add to this the recognition that water is much more common than previously appreciated, solar moons, asteroids, exoplanets, atmospheres, and more, and if you add to it also the focus of Mars, which intensifies, you come to the conclusion that a fresh evaluation of life biomarkers and reshaping of future life detection aims are therefore needed. And our focus will be chiral indicators. Well, in fact, a year and a half ago, you were exposed to an excellent lecture on this series by Daniel Glavin and Aaron Burton, following an excellent review in Chemical Reviews. So I hope to add a few ideas or notes on whatever you already heard from this in that lecture. Okay, so talking about the chirality as a key indicator. The only example that we have is based on planet Earth, and if we take that example, then the chiral characteristics of life are basically 3. First of all, most biomolecules are chiral. Second, quite often the 2 enantiomers occupy the biosphere in unequal amounts. And third, then these enantiomeric imbalances can be grouped into isostructural homochiral families. And I'll talk a little bit about homochirality. And here you can see an example of many natural biomolecules in nature, not only amino acids and sugars, but many others, in which you can find in nature the 2 enantiomers, each functioning in a different way. And so we should ask ourselves which of these 3 characteristics can be regarded as a universal indicator for life in the context of extraterrestrial life. So let me start, first of all, with the universal origin of chirality and various scenarios of enantiomer ratios. It is easier to form chiral molecules compared with achiral ones. I know that this sounds may sound a little bit strange to people who think that chiral molecules are an exception. Well, actually, the opposite is true. Is the true, and the reason is the following: achiral molecules must have improper rotation symmetry, which means reflection mirror, inversion symmetry, S4 or higher, even S rotation symmetries. Now, this is a very strong structural restriction on molecular shape because you require that molecule to have a reflection mirror or an inversion. And here you can see a few examples of achiral molecules. That molecule must have that reflection mirror in order to be achiral. That one must have a reflection mirror to be achiral, and so on and so forth. So chirality, therefore, is a natural universal outcome of the increase in molecular complexity. So if we look, for instance, at the collection of these early prebiotic molecules, or all are small or are of course achiral, and then over the eons, as the evolution and or prebiotic evolution emerges, we get complexity and chirality emerges. L-cysteine and D-cysteine and many other more molecules. So one should keep in mind that chirality develops together with the increase in complexity. Now, of course, when you form a chiral molecule, you form both of the two enantiomers. And then the question is, what can we say about the ratio between these two enantiomers? And we shall see that we can have four distinctly different cases of resulting enantiomer ratios. The first two are, of course, well known, and I bring them here only for sake of completion. So for the first case is the elementary situation in which there's no preference. You form a racemic mixture, and here we see an example of the interstellar formation of glyceraldehyde, which should lead to a racemic mixture. And actually, I remind you that the very definition of what is D and what is L is based on the two enantiomers of glyceraldehyde. Then we have case two, which begins to be interesting. And this is the case where you form when you look at the two enantiomers and you find an enantiomeric imbalance. There is a host of abiotic causes which lead to that situation. And shortly I will detail these causes. But as an introductory example, actually a remarkable introductory example, there is the clear L excess of isovalene in Murchison and other meteorites found by Pizzarello, Glavin, and many others. And I'll come back to that only in the middle of the lecture and also at the final slide of the lecture. Now we come to something which is less known, and I'll devote 2 or 3 slides for that. And that is the situation of chirality, which forms as a result of randomness. So randomness as a source of chirality, which leads to single enantiomer chirality. What is that? Have a look at that tree. That tree is, of course, chiral, okay, because it has no mirror symmetry. The only way to get the enantiomer of that one is to take the picture and artificially revert it, to get the virtual enantiomer. Now, that is a very interesting type of chirality because it's a single event. There is not a second object that looks like that, and it has no enantiomers. We call this one incidental chirality. It's not inherent chirality like the chirality that forms in biological systems. And what characterizes it has no counter enantiomer, and you have no chance to find a duplicate of that chiral molecule. It is also, of course, in the molecular level. Any random polymer like this PDMS is again an example of randomness as a source of chirality. What is the link to astrochemistry? Well, the link are the tollings, which are large molecules, and all of these, which are of incidental chirality. And I remind you that these are formed as a result of irradiation of sunlight irradiation. complex organics are formed of several hundreds Dalton or even thousands of Daltons. And I find it nice to record that the word toluene was actually proposed by Carl Sagan. And so how do these toluenes look like? I copied the pictures from a person who studied these toluenes quite a lot, Sun Kwok. And here are two figures from his papers. And again, notice that these toluenes are of incidental chirality. And there is no left-right preference of the chiral centers. Here's a chiral center of the whole. Each large toluene molecule, like this one or this one, is unique, appearing only once, or at least it is very rare. And there is no enantiomer for that molecule. Case 4 enters bioevolutionary processes, and the picture changes completely. It changes completely from several points of view. First of all, we know from planet Earth that evolution prefers and dictates enantiomeric imbalance. And we know that single enantiomer chirality exists. In a moment, I'll talk about this example, but it is not incidental, even for very large molecules. So if you look at this highly complex chiral molecule, lysine, yes, it's unlike random toluenes, this molecule is produced in exactly the same structure in Avogadro numbers. So this is distinctly different from what we have seen in the previous case. This enantiomeric imbalance actually has several key parameters that we should keep in mind. First of all, it characterizes a very large library of chiral molecules. And this one is a little bit difficult and elusive, so I'll try to explain. The enantiomeric imbalance exhibits features, elusive, of time-evolved sequence and related handedness. What do I mean by that? We look here at the citric acid cycle. So if you find in a certain location, you find the citrate and this molecule, and isocitrate, and then you find this ketoglutarate and so on, which are highly linked in structure, okay? And you get the feeling that they are linked together either in a time-evolved sequence and definitely in related handedness. That should tell you something. Now, it's very difficult to quantify or to tell how to identify it, and you need chemical intuition for that. But I think that any trained chemist who would look at a selection of such molecules will tell you, hey, there is life there. And therefore, both of these parameters are strong life indicators. The second concept, which is widely used in the context of astrobiology, is homochirality, and let us evaluate this concept. And first of all, let us remind ourselves what for the definition. So homochirality refers to a group of structurally related chiral molecules, all of which carry the same handedness label, left or right. And it is an extremely deep paradigm. Actually, I do not understand why the paradigm is so deep, and I'll read you just two quotations out of hundreds maybe. So homochirality, every naturally occurring amino acid is left-handed, while every sugar is right-handed. And this appeared in PhysRev letter, which is a respectful physics journal. Life exists in a single-handed form. Sugars are exclusively right-handed, amino acids are left-handed. This single-handedness is homochirality. No homochirality, no life. And this appears in a publication of the Royal Society of Chemistry. Is it so? No, a big no. Natural amino acids, for instance, D-amino acids, are extremely abundant. D-valine in bacteria and fungi, phenylalanine in snails, D-aspartic acids in humans and snails, D-serine in humans, and many, many, many more. There are at least 150 proteins which contain the two enantiomers of the same amino acid in the backbone, okay? And here's just one of many, many examples. Gramicidin, okay, it's a natural occurring biocidal agent. And that biocidal agent contains, you can see it here, divalene and L-valine and divalene, all together in the same molecule, okay? A similar picture of the role of both enantiomers in practically all families of biomolecules, including sugars, is a real picture of what happens in the biosystem of planet Earth. And this includes the biosynthesis of such molecules, dedicated enzymes for such synthesis, specific functions, specific metabolisms, and so on. Here's another extreme example. The sugar ribinose appears exclusively, or is more abundant in its L form and not in its D form. Now, I could spend the whole talk about this topic, but I want to move on. So you can get the full picture from a review that I published this year, and the reference is here. I'm not the first one to draw attention to that situation. Many others did it before me, and as I said at the beginning, I still do not understand why this is such an extremely deep-rooted paradigm still in biology and in life sciences. So life on planet Earth is not homochiral. Why is that important? Yes, some key families of biomolecules are characterized by high and varying enantiomeric imbalance of the family members, like the amino acids and the sugars. But life is often supported by the two enantiomers at various ratios, is a game changer over life exists in single-handed form. This is the paradigm. This is what should be said. And when you make that distinction, then you recognize immediately that any level of imperfect homochirality must be considered as a probable biomarker of life. Okay, so having in mind that evolution utilizes both enantiomers in imperfect homochirality, what are the other factors that may lead to an observed non-zero enantiomeric axis value? In other words, if perseverance is sending us this message, hi, I found alanine with 22% enantiomeric axis. What is that message meaning? What is behind this number of 22%? So let us get ready for that message when it comes. So part four of the lecture is factors affecting apparent enantiomeric axis. And let us start with abiotic processes. Then we shall move to biotic processes. In abiotic processes, we have enriched, first of all, the enrichment of the enantiomeric axis of an initially racemic mixture. This is well known. These are experiments carried out in laboratories. Here is an example of an experiment carried by this French group, in which left-handed and right-handed circularly polarized light created imbalance in the enantiomers of alanine and in a mirror image. The right-handed preferred the D enantiomer, left-handed preferred the L enantiomer. And in the cosmos and in the galaxy, we have plenty of such sources. Here is one of the recent gamma ray bursts objects, which provides polarized light. And coming back, for instance, to the isovalene excess in meteorites, one of the leading ideas is, as many of you know, that an external chiral field, perhaps circularly polarized electromagnetic irradiation, was involved in the early solar history of the formation of amino acids. So this is one abiotic process. And the second one is the complete opposite, lowering an initial high enantiomeric excess by racemization. And there are many factors that can do it. pH, heat, solar or stellar radiations. And okay, let us come back again to isovalene. So if the L excess represents a process affecting amino acids in general in the early history of the solar system, why then not all meteoritic amino acids show consistent L excess? And the ongoing proposed answer to that question is that many more amino acids were indeed affected at the early history of the solar system and were enriched in L, but that excess racemized over the eons, and isovaline is an exception because it has a methyl group here, which makes this mechanism of racemization very, very difficult. I should add in parentheses that, okay, well, but many of the L-excess meteoritic amino acids, which we shall see shortly, are normal with alpha hydrogen. So I think that explanation for that phenomenon are still should be refined. The process of racemization is also extremely important for the following reason. Because it may affect enantiomeric excess, which we identify in exoplanets, so that racemization of initially high enantiomeric excess is relevant not only for the meteorite enigma, but also for detected old, fossil, and extinct life. Time has passed, and whatever enantiomeric excess was there was blurred by the racemization process. Only a few seconds about this one, because this is something that I'm not sure about, and we are working about it now. Many of the meteorites contain chiral minerals. And there is the process, we are again in abiotic processes, which is called enrichment of enantiomeric excess by spontaneous deracemization. This is a well-known phenomenon in molecules, crystals, interfaces, and so on. And one of the most important mechanisms is the Ostwald-Widmer ripening mechanism. And because in meteorites, even in Murchison meteorite, there are minerals such as belonging to the serpentine family. And the serpentine family contains several chiral variants. Here are 3 of them. I'll not try to spell out how to but all of them are iron and magnesium silicates. I'm not sure about it. I just bring this slide here as in order to make the whole picture complete, and we are working now on that problem. Let us move now to biotic factors, and in biotic factors that other than evolution, we find several interesting situations. First of all, we have to consider planet-wide enantiomeric imbalance. What do I mean by that? Let's take, for instance, these 2 molecules, carbon. Right-handed carbon is found in spearmint. Left-handed carbon is found in caraway. In this, and these are completely different plants. So it depends where you make your analysis. If you make your analysis, if you have some rover probing a spearmint area with several plants, the conclusion is that that planet contains only carbon. You move 100 kilometers away, you find a different plant, and then you suddenly have the S carbon. So the point here is that one spot analysis may be insufficient to do conclusive results, and the best is to have a multiple location spots to get a complete picture of what happens on that planet. So, and the 5th parameter we just talked about, so I'll skip it, and this is that the life forms which use both enantiomers, we have seen it on planet Earth. I'll not spend more time on that, but I want to emphasize 2 additional aspects of the idea of life forms which can use both enantiomers, and here they are. First of all, we may be in a situation of detecting embryonic life. Unclear pattern, enantiomeric access patterns may characterize a planet that is doing its first embryonic steps in attempting to establish life. Testing or tasting, if you want, both enantiomer. This is so for particularly so for a scenario of multiple location simultaneous life emerging attempts. and less so for scenario of life emerging in one spot and spreading all over. So this is one a second comment about life forms which use both enantiomers. And the second one is more science fiction, in my opinion, but it should be listed. And who knows, maybe it is reality somewhere in the galaxy. And this is the following situation. Two parallel biospheres based on opposite sets of enantiomers which live together in peace and which are of some relative different abundances, equal or not, and either totally transparent to each other or with some mutual interchange of eating each other. And having this in mind, one should be very, very careful regarding the following situation. What do you do when you encounter your enantiomer? How do you react to that? Think about it. Okay, let me come to some comments on enantiomeric access, handedness labeling, and homochirality. Again, what should one be careful about? Comment number one is about the need to quantify homochirality, and the reason is the following. It is more probable that we shall encounter gray level homochirality rather than the absolute one and an absolute one. And therefore, quantification of the degree of homochirality is needed. All of this is known to you, so I'll skip it. And I made a proposition. It's not perfect, but it's the best I could think about, and I'm open to other ideas. So the level of an enantiomeric excess of a homochiral set, which is imperfect, is the following. If there are I components, each of which has a relative weight of AI, so that the sum of all weights is 1, then the enantiomeric excess of the group, of the homochiral group, should be something that looks like that. Again, it's a proposition and open to perfections or comments and so on. The second comment that I want to make is about the fact that the enantiomeric excess does not rely on handedness definition. The fact that it does not rely on handedness definition is a weakness, but also a strength. Let me start from the weakness. The weakness is the following. Since the enantiomeric excess is defined in its simplest way as written here, similar enantiomeric excess values may reflect an LD situation in one meteorite and a completely opposite DL situation in another meteorite. And I discussed it with several people. We are limited in the standard definition of what is an enantiomeric excess, and there's no way around it. The strength of the fact that the enantiomeric excess does not rely on handedness definition is that the definition of handedness is extremely problematic. And let us see it in the next comment. It is so problematic that the membership in a homochiral set depends on the definition of the handedness. Let us remind ourselves what is the definition of chirality, the original one, which is still rock solid and serves very well until today, of Lord Kelvin, 1904. I call any geometrical figure chiral and say it has chirality if its image is in a plane mirror, ideally realized, very interesting, the ideally, I'm not commenting on that now, cannot be brought together to coincide with itself. Notice that Kelvin says nothing about the labeling of the handedness. He says nothing in the definition about what is left and what is right. And very, very correctly so, because handedness is just a label. It does not reflect any inherent property. And let us see what that situation causes. So the two main labels that are currently used are the LD convention that all of you know, and the CIP, Kahn-Ingold-Prelog handedness convention. A brief reminder, it's a right-handed if one is the heaviest atom, and 4 is the lightest atom. If you place it like that, it is left-handed if it's a counterclockwise rotation. Okay, so let's take these two definitions which are currently used and see what happens. Let's look at the amino acid L-serine. Under the CIP convention, L-serine, left, this one, a left amino acid remains left, S. But L-cysteine, another amino acid, flips its label to become right-handed when you go from the LD to the CIP convention. And so by just changing the convention of what is left and what is right, you take cysteine and remove it from the homochiral set of all amino acids. So under the CIP convention, cysteine loses its homochirality membership. And here's another example. Let's take the CIP rule. And as I said a moment ago, 1 is the heaviest atom and 4 is the lightest atom. What happens if we make a very slight change? Instead of saying that 1 is the lightest atom, we say that 1 is the lightest group that sits on the amino acid, and 4, the heaviest group that sits on the amino acid, and 4 is the lightest one. So the group that sits on the amino acid is this, okay, all of this. When you make this slight change in the definition of what is left and what is right, then again you are in a situation in which L-tryptophan, which is left-handed, the new definition that I just invented becomes a right-handed molecule. And the fourth comment that I want to make is the following. For each labeling method of what is left and what is right, there is at least one relevant chiral structure for which it is not possible to say if it is left or right. And let us take again the example of the LD convention and the amino acid convention. And you can convince yourself later that if you take substituted cyclic amino acids like this one, all of these biomolecules, by the way, it is not possible to say if they are L or D, because the convention of L or D needs a hydrogen. And the situation here is that we do not have a hydrogen, we have a carbon here and a carbon here. What do? You have to move to another convention to say something about the fact about whether it's left or right. You go to the CIP convention, and the CIP convention tells you that that molecule, for instance, is 1s3r, which tells you that one center is left, another center is right. Is it left or right? You cannot say. It has two centers of handedness. Well, we are not the first to ponder the problem of decision of what is right and what is left. And here we have Winnie the Pooh, who looked at his two paws. He knew that one of them was right, and he knew that when you had to decide which one of them is right, then the other one was the left, and so on and so forth. Concluding slides and some outlook. So bottom line for homochirality. Despite all of the difficulties and the pitfalls that I mentioned, which are just, street lights that you have to keep in mind, look for it. It is a powerful indicator, but do it with care. There are plenty of potential pitfalls on the road, which I just explained to you. If you find it, you've got a strong indicator of life at hand. Or if chirality is there, but grouping into homochiral family is difficult because of the difficulties that I've just explained to you, don't shut the door on life. This is not a situation in which if you are not able to group it into homochiral groups, you say, okay, no way to continue. And the probability that we look at life increases with an increase in the following, which in a moment I'll read it. The idea is that you cannot rely only on chirality, never. You have to look at the complete picture and get a full feeling about it, which is not new. But I felt that it is important to say it because the focus of the lecture is chirality, but you have to get the full picture to make some some educated conclusions. So the probability that we look at life increases with an increase in the richness of the library of detected organic molecules, chiral or not. The non-random complexity of that library. You have to convince yourself that you're not talking about toluenes, but about molecules which have an apparent history of being bioformed. It increases with the proportion of repetitive chiral molecules in that library. It increases with the enantiomeric excess of individual detected molecules. It increases with the global enantiomeric excess of that library, and it increases with the ability to group homochiral families in that library. Not always easy, but in principle possible. I would like to make one slide proposition regarding space missions. Of course, you NASA people are far more experienced than me, but as someone who looks from the side, I would like to propose the following idea. I think that you should consider inclusion of an enantiomeric excess determination of regolite extracts by optical rotation, or ORD or CD. And the reasons are the following. If you determine the enantiomeric excess of that mixture, you first of all get a quick, simple, on-ground yes or no test. It covers all chiral molecules, including unexpected ones and molecules on which you have no idea that they should exist there. You do not have interference from achiral molecules simply because they will contribute nothing to the enantiomeric excess. In chromatography, achiral molecules can appear in wrong places. And it does not require any knowledge of the molecular structure. You just want to know if the extract has some enantiomeric excess or not. So there are two possible outcomes of that experiment. The first one is no, there is no optical rotational signal detected. This is a tentative negative conclusion, but of course continue analyzing. It does not shut the door. But there is a possibility that the overall OR, the optical rotation, and CD signal shows profound enantiomeric excess, and then you are, of course, in a hooray situation. Of course, there are many limitations to that idea, some of which are that it requires pre-concentration and sensitivity, which current methods may need to have some improvement. Let me conclude the lecture with an outlook. To me, and I believe to many of the members of the astrobiology and astrochemistry community, the most amazing natural phenomenon is the meteoritic enantiomeric excess observations. In amino acid, it's well developed, and there are many papers, and I just took one at random by Koga to take some of the values that he lists in his tables. And you see consistently that the L-amino acids are by far more abundant than the D-amino acids. Amazing. And then you go to the study, the pioneering study of Ado Rios and George Cooper on sugars, and you find the same. You find that that there is an excess of D sugars, just like on Earth, in these meteorites. By the way, the fact that this is D and this is L, now we understand is just arbitrary, because it's a matter of how you define what is left and right. So these are amazing observations. And in a nutshell, what these observations tell us. Observation A, solar meteorites exhibit excess of L-amino acids and D sugars. Observation B, life on planet Earth has the same excess, amplified significantly. Hard to believe that these two observations are not intimately linked. So resulting questions are the following. How are they linked? For instance, you know that one of the propositions is that seeding of Earth, kickstarting the specific evolutionary preference of enantiomeric axis imbalance is the link. Second question, is that enantiomeric axis trend characteristic throughout the solar system? If you ask me, the answer is yes, should be. I'll be surprised if this is not the situation. And let us continue with the resulting questions. Is that specific enantiomeric axis preference galaxy-wide? There are three possible answers. No, the galaxy is racemic. How can that be? Local events, like polarized light, are left-right-handed at random. Therefore, resulting enantiomeric axis life imbalance in the galaxy is dictated by the local events and random throughout the galaxy, making the galaxy racemic. A second no is the following. No, the galaxy is racemic, simply because life selects imbalanced enantiomeric axis even in the absence of dictating local events, such as the polarized irradiation. And then there is, of course, a yes. The same enantiomeric axis trend is found throughout the galaxy. And in that case, asymmetry of nature itself or the universe itself enters perhaps the weak force. And the final slide is, well, the answer to these questions, patience is needed. It may take a few hundred years to get the full picture. Thank you very much.
Wow, it's a wonderful presentation, David. Thank you so much. It might take a few hundred years, but hopefully we can disentangle some of this here now. I see a lot of applause reactions coming in. For those watching, if you have questions, you can certainly unmute yourselves or feel free to ask in the chat. We do have some time for questions here. And there's a question actually already from Dragos that kind of is my own question. You mentioned incidental chirality, this idea that there are chiral structures that don't have a mirror opposite. And Dragos is asking a similar question. Should we then consider chiral molecules to only be those that actually have a mirror counterpart in the physical world?
The separation is not if it's a single enantiomer, but if it's a single event. The random chirality and the objects that emerge from random chirality are never repeated. That tree that I showed will never grow again. That polymer folding that I showed will never grow again. That toluene molecule is a one-time event. And therefore, single enantiomer chirality is a highly legitimate member in the biology of Earth and probably elsewhere. And the test is it a single molecule or is it an Avogadro number molecule? That is the test. Not the question if it has a counter enantiomer, but is it repeated?
And it's very interesting. It kind of makes me wonder too about emergent properties for alien life and whether we'd find more of this incidental chirality amongst different kinds of life or less.
Yep.
We have another question coming in from Dragos. Could there be more than two images of a mirror, therefore more than one reflection in terms of enantiomers?
Yes, it's an excellent question. The definition of Kelvin talks about ideally reflected. And in fact, when I said that random chirality has no enantiomers, that is correct. But the more precise sentence is the following: random chirality forms enantiomers for which there is no exact counter enantiomer, but almost similar can happen. Almost similar can happen. So you can, for instance, that tree that I showed. If you walk through a forest, you may encounter a tree that looks the same, has features of the other side, is not exactly the same enantiomer, but is in the vicinity. And the question, the person who asked that question, if you drop me a line, I'll send you a paper or two of that we made on near enantiomers. So near enantiomers in random chirality is possible. Exact enantiomers are not possible.
That's very intriguing. Highly recommend those who are interested reaching out for more. We have a question from Charles Telesco, and this is one that's also, I think many of us are wondering about, given your excellent presentation about the issues in L and D terminology and even R and S terminology being based on group structure around the chiral atom. Charles's question is, isn't that ambiguity of chiral definition then removed if we define L or R based on the interaction with circularly polarized light instead?
In general, to define left and right based on physical phenomena, again, is problematic, and I'll explain why. When you look at the CD spectrum, in most of the CD spectra, there is a crossing at 0, at a certain wavelength. So suppose that your circularly polarized light is at that 0 point. That circularly polarized light will not be able to tell you if it's left or right, because you have just crossed the 0 line. And this is in general. If you take any physical feature as a possible way to define what is left and right, there's always a situation in which it will not work. The simplest example is a chiral column chromatography. Okay, so it can separate enantiomers, but not all of them. So what happens if you take a pair of enantiomers that are not separated by that column? Then you come to the conclusion that that pair of enantiomers is not chiral. So it is extremely dangerous to define handedness based on an experiment. It must be a purely geometrical definition, and even that is problematic. In my opinion, the simplest solution to that is to show the picture of the two molecules and to say, I call this enantiomer 1 and this enantiomer 2. You can say, okay, I call this one left and call this one right. We can make an extremely simple test, okay? All of us know that this is left and this is right, okay? Now, all listeners to this lecture can make a group decision that from now on, this is called left and this is called right, just the opposite. Nothing has changed. The chirality of that one and that one remained intact. The only thing that has changed is the vocabulary, the definition. If you go to Google what is left and what is right by the definition of our group, you'll get confused. But nothing inherently has changed by just saying, okay, from now on, I'll call this one right.
That reminds me a bit about redox chemistry and how many issues I have with the terminology of reduction and oxidation, but it's the process that really matters the most. So maybe we need to get the IUPAC together and revise some of these issues. So we have a question from Ilan Kuzali, who kind of wants to, I guess, maybe have more expansion on this idea of meteorites seeding life on Earth and then having that be the choice of chirality. I'll go a little bit beyond Ilan's question as well. We talk a lot about if we find life on Mars and it has DNA, if it has DNA, especially if it has a similar base sequence to life as we know it here on Earth, then we almost instantly can start to conclude or hypothesize that we have a similar origin. And so if we go to Mars and we find life and DNA or no DNA, if we find life on Mars that has a similar chiral structure to life on Earth, does that also then imply that we have the same kind of origin, Or does it simply imply that we live in the same solar system with a similar starting chirality?
Yeah, I must say that I have an extremely dull opinion about how life looks like elsewhere. And my opinion is that it's not very different from ours. That the solution found or created on planet Earth is some sort of an optimal solution. That if you give a kickstart of a similar chemistry elsewhere, you'll get things which are quite similar to what we see here. I know that it may sound stupid in a situation of 100 billion stars in our galaxy that seem to suggest that the amount of options are endless, but that is my intuition. And so that the science fiction movies that show you aliens which are basically human-like with distorted faces is probably not so far from reality. I don't know if they speak English, but they look like us. And therefore the answer to that question is that if we find similar biomolecules elsewhere, I'm not so sure that it tells something that they were communicated from one place to another. The option that they were that they evolved independently and gave the same solution is, in my opinion, a strong hypothesis.
Very intriguing. We have another question from Tony Rico. Tony, I'm not quite sure I understand your question. Would you mind unmuting to ask your question for us?
Sure. David, thanks for a marvelous lecture today. A lot of good information and ideas. My question was, given that the LD naming convention is in some sense arbitrary, and you showed us how you might come up with a different convention, is it simply coincidental that L-amino acids are predominant and D sugars are predominant in life? Or does the fact that the naming condition relates to the sequence of light to heavy, heavy to light, somehow relate, not exclusively, but in many cases, to how easy it is to build up something like a polypeptide and from that a protein? Even though it's arbitrary, it still relates to what can be made out of those molecules.
Yeah, I understand your question. I think that you can make yourself a self-exercise, switch the definition, and see that nothing in your question has actually changed.
Mm-hmm. Agreed. Yeah. I've done that self-exercise, and I completely agree with what you're saying.
Yeah.
Yep.
Yes.
Okay. That's a good answer.
Awesome. Are there any more questions in the chat, or if anyone would like to unmute themselves and ask another question?
Yeah, obviously, I'm sure that this is needless to say, but anyone is most welcome to simply correspond with me by email or anything else.
Well, I'm going to guess that no one else has any questions. It was a really fantastic and illuminating talk, David. You really have my mind kind of wrapping around now all these possible exceptions, as well as some ways we might, better apply this in the future for life detection, especially as now, many of us from NfoLD and Nexus are involved in writing this white paper about standards of evidence in life detection. There's certainly more work to do in how we define our confidence, how we find confidence in our measurements and when we're looking at life detection. And so, grappling with these issues, as you say, it might take us a few hundred years to get the full picture in these issues, but it's a very important thing for us to discuss now. So thank you very much for your time.
Thank you for the opportunity to give that lecture. It was my pleasure.